in this video, we'll be talking about diagonalization. And the whole basis of diagonalization is based on diagonal matrices. So to go over them quickly, diagonal matrix is just any matrix where you have values along the diagonal. So let's just call it x1, x2, and so on. But all the other entries are zeros. So as you can see with this matrix, calculations become a lot easier because it's either just a number or zero, and you can disregard having to think about and to manipulate a lot of the other entries in the matrix. That's also why with diagonal matrices, it's much easier to determine the properties of, for example, whether they're full rank or not, or whether they're invertible. So the whole basis of diagonalization is to get this representation of this matrix in a diagonalized form so it's easier to use. And this all relates to the bigger picture idea of solving differential equations of RLC circuits because it's another technique that we will need to use in order to solve the differential equations, and we'll see that in the next video. So going into diagonalization, another name for it is eigendecomposition. So with eigendecomposition and diagonalization, the whole motive or the thing you're doing is you're changing to a basis where the linear operator is a diagonal matrix. What this means is say that you start off with a matrix T. You want to find the appropriate basis where if you transform T to that basis, then this resulting matrix that represents the same linear operator will now be a diagonal matrix. And what you'll find out is that the basis you would want to usually change to is the eigenbasis, and specifically the eigenbasis of the matrix. So the example here, it would be the eigenbasis of T. So then based on this change of basis, we can now derive the equation that is mainly used for diagonalization through drawing the same diagram that we kind of relied on in the change of basis video. So in general, you have your current basis, and then you have the eigenbasis that you are changing all the coordinates into. So let's say in your current basis you just have x and y, and then for eigenbasis, I'm just going to call them xe and ye. So you already have this transformation t in your normal basis. That takes you from x to y. But now you need to be able to represent it with the diagonal matrix, which would be in the eigenbasis with the same linear operator. So I'm just going to call it D for the diagonal matrix. So then D will be expected to have all the eigenvalues along the diagonal. So that is how D will be defined. So now we need to see how do you get from your regular basis into your eigenbasis. So going off of change of basis, you would want to have your matrix that you multiply, which is the basis you're going into or exiting at. So let's define the matrix V as your eigenvectors. Then in this case, if you're going from the eigenbasis back to the current basis, you would multiply by V. And if you're going in the opposite direction, then by V inverse. And that goes the same for the Y. Okay, well, earlier we just went directly with T, but now we want to represent T with the diagonal matrix inside. So you would go along this red path, in order to still go from x to y. So then that means t is then equal to, going off of the left multiplying rule, inverse dv. And this is your main diagonalization equation that you want to keep in mind, because you're representing the linear operator t with the diagonal matrix, which is symbolized by the d. And from this, you can also tell that there's a v and a v inverse. So then based on this, you know that v has to be invertible. And what is v? Well, v are the eigenvectors. So the only way that v will be invertible, or in order to ensure that it's invertible, is that this v must be completely linearly independent, which means that there must be n linearly independent eigenvalues. Eigenvectors. And this also just means that v will end up being full rank. And another part of invertibility is that v must be square. So that's what to keep in mind, but you'll usually need to look for the fact that there are n linearly independent eigenvectors. So an example of where a matrix is not diagonalizable because the eigenvectors are not all linearly independent is the matrix 0, 0, 1, 0. So this is not diagonalizable because here you can see that it's already an upper triangular form. So you know that the eigenvalues are 0 and 0, which means that it is repeated. But with repeated eigenvalues, you only have the same eigenvector in this case. So the only eigenvector you have is 1, 0. There aren't two linearly independent eigenvectors. And then because of this, this is not invertible. The matrix V is not invertible, and therefore this matrix is not diagonalizable. So that is the main gist of diagonalization, and just some kind of general thing to keep in mind is that in your diagonal matrix with the eigenvalues, you usually write the lambdas in terms of lambda 1 is greater than lambda 2. So you write them in decreasing order just out of convention, but in general it doesn't matter as long as you match up the eigenvectors appropriately. So if lambda 1 is in this spot, then the corresponding eigenvector has to be in the first slot of the V matrix. And for diagonalizable matrices, they must be square because you need to be able to find the eigenvalues in general. Cool. So went through all of this and got this main equation for diagonalizable matrices. But you may wonder, yes, there is a diagonalized matrix that makes calculations easier, but now it's just a combination of three matrices multiplied together. Is that really easier to use? Does that actually simplify calculations? So a great trait that we are actually going to prove about diagonalized matrices is that if you were to take t, you wanted to raise it to the kth power, this is just equal to v times d to the k and v inverse. And this is super helpful because if we go back and look at how the D matrix looks like, if you were to take d to the k, then that would just be the same as raising all of the lambda values on the diagonal to the kth power, while everything else stays as 0. So this is a really easy calculation to make, especially in comparison to having to multiply the t operator multiple times. But why is this true? Well, if we start writing out the pattern of the t matrix multiplied to itself over and over again, we can start to see. because we have the starting point of t is equal to v dk v inverse. Let's consider t squared. So then v, oh, sorry, there should not be a k here. So sorry, we start off with v d v inverse. Now we take t squared. So then we have v d v inverse times another v d v inverse. Here, you can simplify because in the middle here, v inverse times v is just the identity. It's just itself. And then this just becomes v to the k, since there's two d's now, v inverse. And you can continue writing this for t cubed, t4, and so on, and you'll eventually get to this equation. So this is the main reason and why having a diagonalized matrix really helps with calculations. Cool. So something I definitely wanted to point out is that the fact that something is diagonalizable does not mean that it is invertible. They're two different things. Yes, both of their classifications and their traits require there be linearly independent kind of something. But something to keep in mind is that for invertibility, the columns have to be linearly independent. For diagonalizable, it's the eigenvectors. So that's a brief classification of how the two are different, but let's take a look at some examples of ones that are just diagonalizable or just invertible and not the other. So, for example, let's consider when it is diagonalizable, but then not invertible. Okay, so this means that the eigenvectors must be independent, but there must be some linearly dependent columns. So whenever there is an eigenvalue of 0, then that means there's a non-trivial null space, and hence it is not invertible because it's linearly dependent. But you can still have independent eigenvectors as long as your other eigenvalue is not 0. So a matrix that demonstrates this is 1, 0, 0, 1, 0, 0. So from here you can easily tell that these two columns are linearly dependent, and it therefore has a null space that's non-trivial, and because of this, it is not invertible. But here, you still have two distinct eigenvalues, and it will actually result in the eigenvectors of 1, 0, 0, 1. So hence, it's still diagonalizable. Okay, now let's look at the kind of the opposite. So now let's say that it is an example where it's not diagonalizable, but it is invertible. Okay, so kind of on the flip side, this must mean that the columns are linearly independent, but there's the same eigenvalues, because remember, if you have the same eigenvalues, then that causes the result to be just one eigenvector, and you no longer have a full rank of independent eigenvectors. So an example of this is 1, 0, 1, 1. So based on these two columns, you can tell that they're linearly independent and is therefore invertible, but you can see that both eigenvalues are 1. So since both eigenvalues are 1, there ends up only being one appropriate eigenvector, and that's why the eigenvector, the only one that exists, is 1, 0, and there's no longer two linearly independent eigenvectors, and therefore is not diagonalizable.